Okay, this section we're going to look at reduction of nonlinear laws to linear form, and you can have lots of different equations like y equals ax squared plus b. If you add some data, you can see you compare that with the classic y equals mx plus c. If you wanted to draw a curve, then that would be your x, wouldn't it? And this would be your y. So if you plotted that arrangement on a graph of x and y, then you'd get a straight line, wouldn't you? And you'd be able to work out a and b. So you probably have some data once you plotted it of these two things, and you could draw a straight line through them as a best fit, and then you could read off the gradient by drawing a triangle onto the curve conveniently, and you could read off the intercept value as well, and you would get a and b, and you could find the linear form. Similarly, lots of variations on the same theme. So another common one is y equals a over x plus b. Here you could write that as y equals a lots of 1 over x plus b. This time this would be your y. You choose these data points as your y-axis and 1 over x is as your x-axis, and if you plotted that graph, so basically plot the x against the y this time, you'd have a straight line. Same thing applies, and you could read off the gradient and intercept and find these values. Okay, good. Another one, there's quite a few of them. Say y equals ax to the n. Here you could take logs to any base, so log y is equal to log a, and then it's times log x to the n, which you can write as n log x. And we can write this as n log x plus log a, and this is log y. So if you're plotting points, if you had data points, this would be the y, and then this would be your x-axis. So you'd plot log against log, and you could work out the gradient and intercept again, couldn't you? The gradient would be n, the intercept would be a, and you'd find the relationship between y and x then. Best explained by examples, but it's just good to list down the variations before we actually do the first example. The next one, there's another one here. There's a few more. So let's have a look at the next one. Y equals a e to the bx. Because this is power e, it's good to take logs to base y, because there's the power is e to the bx. So natural log of y is equal to natural log of a plus, and this is in the air, so it would be bx log e, wouldn't it? When we simplify the logs. Log e is 1, so this is simply bx plus ln a, and that's ln y. So you'd plot y equals bx, so you'd plot log y data points against x data points as your y and your x-axis here, and you could read off the gradient, which would be b, and the intercept, which would be log a, and then you could work out a value, you know the b, and you could get the relationship. And there's one more, y equals, that's mentioned, a times b to the x. So here take logs again, log 20 base, log y is equal to ln log a plus, and it'd be x log b, wouldn't it? Which you can write as log b times x plus log a. Again, you'd have to plot log y against x on a graph to be able to unfit the data points. You'd have your data points, fit the best line, and you could read off, just draw any convenient triangle, and you could read off the intercept and work out this value for the gradient and this value here for the intercept, and you could work out b and a and determine the relationship. Okay, so let's clear all this now. Now we've reviewed that, and we'll look at the question itself here for the first example. Okay, here's the question then. I've just pasted it in. I've got the data here, and it's thought that these two, this is the distance of the planets, this is the period in days that they traverse the solar system, and basically it's thought that it's understood that the log of the distance and the log of the period have a linear relationship. So we could take the logs of all of these and we could put them down here and here and plot log against log and see if there's a linear relationship, because we could read off the gradient and the intercept and then determine that. So that's what we're going to do, but we're not going to go through the full example. We're just going to do a couple of simple little points because it's believed that they all lie on the line or near enough, and we're going to just use 2 points and suppose that they're really accurate points and actually lie on the line itself. Because you would draw a best fit line normally and you'd approximate it. You wouldn't actually use necessarily 2 points unless they were perfectly on the line. So we're just going to make that assumption to make this example simple to explain. Also, we're not going to draw it to scale because it says plot, and I've just done a sketch because I'm using a digital pen, so you'd need graph paper for this, of course, as well. So let's get those 2 points then. I've marked them here, Venus and Neptune. So we'll need the log of Venus, won't we? Which is the second one down. Log base 10 of 108.2. 2.03. So I'll put that here. 2.03, and the log of the distance 225, 2.35. Okay, and then we'll do Neptune as well. We'll write it 2870, wasn't it? No, 4497. Log of 4497. 3.65. And log of 60150, then the distance 60150, 4.78. And these are the coordinates. I've just done 2 of them. We could do them for all. We mark those coordinates on the axis. If you can see them here, there's Venus here and Neptune here, and I've got them here, and I've drawn the line supposing that they're precisely on the line. You do the line of best fit. Then we can simply read off the gradient. Again, I'm just going to read off the gradient from these 2 coordinates rather than, because I haven't got graph paper, so it's easy to do that. And you could read off the intercept. Now the intercept goes down here, and you'd have to extend this line here and read it off. Now my sketch isn't that good, so I'm going to use the value that they've got for the intercept. Oh, okay, well they've used the data. They've used the data itself to get the line. So they've got the gradient, and the gradient goes through a point, and then they've worked out rather than read it off. So I will do that as well then. Just use these 2 points to get all the information. So here the gradient, the m value is equal to the difference in y, 4.78 minus 2.35, divided by the difference in x, which is 3.65 minus 2.03. Type that in the calculator then. Let's quickly do that. So on the top is 4.78 minus 2.35 divided by bracket 3.65 minus 2.03 equals 3 over 2, or 1.5. So there's our gradient then. Now we know that this line will be, I'll use capital Y equals m x plus c. Here's our straight line. We know the gradient is 1.5, so capital Y equals 1.5 x plus c. Here's the capital X, and here's the capital Y. Okay, now it goes through, let's say, this point here, for example. So let's have a look at it then. So y is 2.35 equals 1.5 times x, so I'll just put a bracket around them, times 2.03 plus c. So c will equal the 2.35, I'll tap that in the calculator, just work it out straight away, minus this number which you take over, the 1.5 times 2.03. It should be a negative number, minus 0.695. 695. So we can see then that y is equal to 1.5 x minus 0.695. So let's go back to the logs then. This was log of the distance and the period, wasn't it? So if we label this axis here as the distance d, and this is the period p, then we can write down this. So log of the y-axis was the distance, wasn't it? The y, period, and dist. So the 2.35 was the period. 2.35 was the period. So this is the period, and this is the distance as marked on the axes. So log 10p then. This base 10 we're using is 1.5 log 10 of d minus 0.65. Okay, so what have we got here then? 695. So, okay. What log 10 is that? We better do a shift log on that to write that as log. Shift log then, or so to undo a log, you shift log, which is a power e, minus 0.6. Oh, base 10 we're doing. Shift log minus 0.65. 695. That's undoing the log. 0.201. So we'll call it 0.2 then. And it's plus 0.2. The log of. So it'd be log of log 10. So I just worked out what value that corresponded to. Let's just check it. So log 10 of 0.2. So log of the answer, the 0.2. And you get your back to minus. So that's how you go from the number to the equivalent logarithm on the calculator. So here this is added and this is a power, so we've got log p is equal to log d. Move this up to the power 1.5 plus log 10 0.2. Now we can write that as log p equals log plus you times you add, don't you? So this is 0.2 times d to the 1.5. And then the log of this equals the log of this, so now we can undo the logs, can't we? Just write p equals, because the values must be the same. 0.2 d to the 1.5, and that's how you do it. And there's our relationship between the period and the distance for the planets in the solar system. Okay, so that's the example there.